Okay, let's start our second topic.
I would like to thank the organizers for the wonderful work and for the kind invitation. The title of my talk is on the space-time monopole equation. This is actually a very old field to work with Chuu-Lian and Terng Uhlenbeck. There are two reasons. One reason is that I left the integral system for a very long time, and another reason is that this is a very interesting equation in gauge theory and integrable systems. And so perhaps there are also some related questions to work on it again. So here is the main content of my talk. So I will talk about some basic theory on gauge theory and two classical methods in integrable systems. So here is some basics on gauge theory. R4 is a four-dimensional vector space with definite or indefinite metric. So actually, I will consider three types of metrics. Euclidean 1 and the other two with signatures 3, 1 and 2, 2. And the volume forms are always the wedge product of dx1 to dx4. And the Hodge-Star operator maps P forms to 4 minus P forms, and it's defined by the integration. So it depends on the metric and the volume form. And here G is a compact Lie group with Lie algebra and bi-invariant metric. And we will also consider a principal G bundle over the base manifold. So here is basically triple. But if we impose boundary conditions in the topology on the principal bundle, and N is connecting, so it's the algebra valued one form, and the FA is the curvature. The Yang-Mills functional is essentially the L2 norm of the curvature. So it's well defined. The pointwise norm depends on the metric on the base manifold and on the Lie algebra. And then the critical point satisfies the Yang-Mills equation. So it's the dA star FA equal to 0. So this is a nonlinear equation, and it's also gauge invariant. So this is the basic equation in gauge theory, and the curvature always satisfies the Bianchi identity. So we first consider the two cases where the matrix is the Euclidean one, and the other one is called ultra hyperbolic. So in these two cases, the Hodge-Star score is equal to the identity on two forms. So the self-dual and the self-dual two forms, and there are the so-called anti-self-dual Yang-Mills connections on R4 or on R22. So the equation is star FA equal to minus FA. So by Bianchi identity, such connections are solutions to the Yang-Mills equations. Actually, they are minimizing solutions. So these equations are fundamental in gauge theory and also in integral systems. So the other case is on the Minkowski space-time with Lorentz metric. in this case, star score is equal to minus under the on two forms. So in this case, there's no self-dual or anti-self-dual solutions. For Yang-Mills equation on R1 is an important equation in physics, and is also extensively studied in mathematics. The main method is analysis under PDE. So I would like
What is the square of which there is R22? Also one?
also one. Yeah, so now self-dual or anti-self-dual solutions. So I would like to say the Euclidean case and the Lorentzian case are interesting. In the Euclidean case, the under-self-dual Yang-Mills equations are defined on smooth four manifolds, and then the solutions are called instantons. And the moduli space is used by Donaldson to define its polynomial invariance. And so for the Lorentzian case, it's fundamental in physics. So in the R22 case, it seems not very interesting. So I think here are 2 points. One point is that it could be interesting to have actual dimensions in space direction. So in string theory, there are actual dimensions in the space direction. So it's still possible to have actual dimensions in time direction. And the other reason is that there are some interesting reductions from the Yang-Mills equations on R22. So if the connections is invariant under translation along the x4 direction, that is, if the coefficients are independent in x4, then the unself-dual Yang-Mills equation reduces to the monopole equations on R3 or R21. So the equation is dA5 equal to star FA. So here the first three components comprise a connection, and the A4 becomes a Higgs field, and then the Hodge star is defined by the metric on the three-dimensional space-time. And the interesting solutions decays at spatial infinity, and they are called monopoles. There are some basic properties of the monopole equation. One is that they are invariant under gauge transformation. So the other one is that they are invariant under the fundamental groups SO3 or SO21. So hereafter we will consider monopole equation on the 2-1 case. And this is interesting integrable systems of a hyperbolic type. And it can be reduced to some other integrable systems, such as the Watt equation or modified 2+1 chiral model, so which has 4 terms on the left-hand side. Actually, the first 3 terms is called the 2+1 chiral model. Right? But unfortunately, it's not integrable. Okay. So Watt find this equation from the reduction of unacceptable equations on R22. Okay. So this is a modification of the 2+1 chiral model. And it can be further reduced to 2D chiral models or 1+1 chiral models. When the map J is independent of T, then it reduces to the harmonic map equation. And if the map is independent of Y, then it reduces to the 1+1 chiral model. So such reductions were first studied by Watt and Uhlenbeck.
And what is the reduction to J? what they need to do is monopole equation to have this work equation.
Yeah, this is a good question. So this reduction is called gauge fixing. So if we have the monopole equation and it has a next pair that I will introduce quickly. Then if we fix gauge at infinity in the spectral parameter, then we will get this one equation. So this is called gauge fixing. So let's introduce the next pi equation for the monopole equation. So let Z be the complex variable, and the xt is the x3. So the monopole equation is equivalent to this next pi equation. So as these two operators, actually this next pair is reduced from the next pair for the interceptual Yang-Mills equation on R22. So for the interceptual Yang-Mills equation, it has a next pair, and it's so now for the x4 variable, we change the covariant derivative to the scalar Higgs field phi. Then we get this next pair. Just now the question is that we can fix the gauge at mu. Fix the gauge at mu equal to infinity. Then we will reduce to the Watt equation. So if we do a linear combination of the two operators, we get an equivalent next pair. The next one depends only on the space variable, and the other operator describes the time evolution. So this is also understood as a zero curvature equation. So it's the compatibility condition of auxiliary linear system. So this capital E is called parallel frames of the linear system, or more actually, for the first equation, it describes holomorphic sections of certain vector bundle. So here E depends on the space-time variable and the spectral parameter mu, and takes values in the GLNC. And O is an open subset of the spectral plane. So here, after we fix the structure group G to be UN, the main reason is that we will use loop group method. So for loop groups, the UN case is the simplest one. For other types of compact E groups, the loop group theory is somewhat more difficult. So if E is a solution of the auxiliary linear systems, then U bar inverse take permission conjugation and take inverse is again a solution, because the main coefficient is in the linearity the UN, so it has such kind of symmetries. So we require E satisfies this condition. Mu bar inverse star times E mu equal to identity. This is called UN reality condition. Solutions E of the linear system that satisfies the UN reality condition and the boundary condition. That is when that tends to the space infinity, E goes to I, are called monopole frames. So now we go to the second part. We will review the scattering and the inverse scattering transformation for the space-time monopole equation. This is due to Malakov-Zaharov, linear focus, and little under honors. Actually, we will see for this space-time monopole equation, the inverse scattering transform and the Backlund transformations works very well for this system. So first we fix time t, and for any spectral parameter mu outside the unit circle, the operator ds, which is mu Laplace z minus mu inverse Laplace z bar plus alpha. This is a partial bar operator in a complex variable w, which is related to the z by this formula mu inverse z plus mu z bar. So it defines a rank n holomorphic vector bundle on the Riemann sphere. Now the complex variable is w. So when the W21 norm of A phi is small, we hope that L mu is holomorphically trivial for most mu, which is outside the S1. So here, W21 is the Sobolev space, Sobolev space of maps whose second derivatives are L1. So in this case, we can solve the following problem by analytic method. So the first one is a partial bar equation, and the other two are boundary condition and the reality condition. We can solve this problem by iteration method. So we are interested in those frame E whose limit exists as the mu tends to the unit circle from inner side. So a spatial pair A phi is called to have continuous scattering state if the previous system has solutions in mu plus minus, which is holomorphic in one side neighborhood of the unit circle. So in the outside neighborhood, the norm of mu is greater than 1. In the inside neighborhood, the norm of mu is less than 1. And we also assume that the limits exist when mu turns to the circle from outside or the inside of the circle. So for the because of the reality condition, S theta minus is equal to the S theta plus star inverse. And we define S theta in the product of S minus inverse and S theta plus. So this is called the scattering matrix. And so here is a map from space times fixed time t times the variable mu in the unit circle. The value is Hermitian symmetric and positive definite. And as xy tends to infinity, the S theta tends to the identity. So here is the result of Villarreal focus and the ion needle. If A phi decays at the spatial infinity and small in W21 norm, then the vector bundle L mu is holomorphically trivial for all mu outside the unit circle. Moreover, the continuous scattering matrix S theta satisfies this simple first order linear PDE. So this is the simplest one for the scattering matrix. So we can solve this first order PDE. There is a small s such that the scattering matrix is defined by this simple form. So now we consider the time evolution of the monopole equation. So if A5 is a monopole and has smooth continuous scattering matrix, then we can it satisfies this first order PDE. So we can solve it, and it has a simple form. So the scattering data evolves in a simple way. We can solve it easily. So to return to solutions, so we need to solve certain Riemann-Hilbert problem. And so the next step is the inverse scattering transformation. So given a scattering data which is defined by this form, and ES takes values in positive definite Hermitian matrices, we want to factor S theta as a product of these two forms, mu minus, which is the limit from the inside of the circle, and the mu plus is the limit from the outside. So to solve this Riemann-Hilbert problem, we use Iwasawa decomposition of loop groups. So we put P mu equal to square root of S theta. Because S theta is positive definite, we can take the square root. And for this loop, we use Iwasawa decomposition of this loop. So we decompose it as the products of u mu times e mu plus, where u mu is a loop which takes values in the unitary group, and the e mu plus is holomorphic outside the unit circle. So outside the unit circle, we have defined the e mu plus by the Iwasawa decomposition. So inside the unit circle, we use the UN reality condition. So it's defined by the reflection. Then this e mu is a monopole frame with scattering matrix. So which is just the P mu square is SC is the original scattering data. So just now we described the scattering and the inverse scattering transformations for the space-time monopole equation. Actually, the result is as simple as what we expected. So it's just to understand the auxiliary linear system carefully and solve partial bar problems. So in this, in the third part, we will construct solid form solutions of the space-time monopole equation. Such solutions have discrete scattering data. So in this case, it will be better to change variables. So we will use the spectral parameter lambda. So it's a transformation from the unit disk to the upper half plane. And we will introduce light cone coordinates psi and eta. So the linear system for monopole frame is equivalent to that one, use lambda and light cone coordinates psi, eta, and the variable y. And the reality condition is f lambda bar star times f lambda equal to the identity. So by theorem of Uhlenbeck, for loop element which satisfies the UN reality condition, the simplest one has this form I plus lambda minus alpha, and actually the alpha minus alpha bar over lambda minus alpha times pi curve. Here, alpha is a non-real complex number, which is the simple pole, and pi is a Hermitian projection of Cn, and pi curve is the orthogonal projection. So rational elements satisfying Euler reality condition can be factorized as a product of such simple elements. So one solitary monopole frames has the following simple form. So it has a simple pole and depends on projection. So a priori, this alpha and pi may both depend on space-time variables. But if it's a monopole frame, then this pole has to be constant, and the projection depends on the space-time variables. But it satisfies a simple system of equations. So the image depends on a holomorphic map from S2 to some Grassmannian. So this determines the projection pi completely. So we find the monopoles, one solitary solutions for the monopole equations. Now we can have so-called Backlund transformations. So suppose F is a monopole frame holomorphic at some point lambda equal to alpha, and then with this alpha we can choose one solitary solutions. So the frame G alpha pi has a simple pole at alpha. Now the Backlund transformation is to consider F1 of this form. So we need to find pi tilde and the F tilde. So here pi tilde is the Hermitian projection onto this vector space. So it's F evaluated at lambda is equal to alpha, then applied to the image of pi, and then F tilde in this form, G alpha pi tilde times F times G alpha pi inverse. Then this F tilde is holomorphic at lambda equal to alpha. So with this property, the F1 written in this Gaussian form, G alpha pi times F equal to F tilde times G alpha pi is again a monopole frame. Okay. And this is denoted the Backlund transformation of G alpha pi on F. So this is actually a traditional one, and it's actually a very simple form. The proof is somehow a simple complex analysis. Now, applying Backlund transformations on one solitary frames repeatedly, we can obtain rational frames with simple poles. That is, if we let G alpha I pi I be a sequence of one solitary frames with distinct poles, then we apply Backlund transformations repeatedly. Then we get multi-solitones whose frames have simple poles. So next step, we want to find solitary solutions whose frames has poles of higher multiplicity. So this is a limiting method developed by Terng and myself. So the method is that we fix a pole alpha and let Bi be a sequence of rational maps from the complex plane to Cn. And for small epsilon, we let alpha epsilon be alpha plus epsilon. So this will be a nearby pole. and Fk epsilon is this this Tyler polynomial with coefficient b naught to p minus 1. And then let pi k epsilon be the Hermitian projecting onto the compass line spanned by this Fk epsilon. Okay. So it depends on the variable in this form. Now, when let F1 be the first one solitary frame, and for Fk, we use this inductive limiting method. So first, we apply Backlund transformation by G alpha epsilon pi k epsilon on Fk minus 1. We will get k solitary. And then when we let epsilon tends to 0, we get k monopole whose frame has multiplicity k at the pole alpha. Actually, the idea is a simple one, but we need to approach the limit carefully. So actually, only a higher order term entered to the k solitary. So this is an interesting and careful limiting method, and it's very interesting. And if we for other limiting method, actually you cannot get non-trivial solutions. So before our work, and I only tried some symmetric limiting method. We can only get solutions with double poles or triple poles. So using this limiter method, we can construct all the solitary solutions. So apply a generalized Backlund transformation. So we can use this higher order pole solutions to make Backlund transformation, and do this repeatedly. We can construct all solitary solutions up to gauge equivalence. Yeah. Now we can combine the Backlund transformation and the inverse Backlund transformation together, and we can get space-time monopoles with continuous and discrete scattering data. So by combining the Backlund transformation and inverse scattering transformations. So So I introduced the two traditional methods in integrable systems. So the one is inverse scattering transformation, and the other one is Backlund transformation. We see that these two methods work very well for this monopole equation, and it also works well for the water equation and the chiral models in 2D and 1+1 dimension. So this is the end of my talk. Thank you for your attention.
Questions?
Here, which kind of solution you define as a solid solution?
So which means the frames are rational in the structural parameter.
Okay.
Yeah.
And the server of Uhlenbeck you mentioned that something can be decomposed into concentric factors. That decomposition is unique.
That means so basically it's not unique because the order of the product. So but let's call the permittability. That's okay. So when you if you switch alpha 1 and alpha 2, the two poles, then you can work out. That's okay. And so besides this, I think the the decomposition is, I think the decomposition is unique.
Okay.
Yeah.
Okay. Thank you.
Okay, if no more questions, then send the speaker again. Have lunch in 20 minutes probably. Or the. Okay. Not later. But first we need to finish coffee break.